This time we will talk about section 3.4, which is equivalent statements. So still talking about logic, and actually a lot of this we will still use truth tables, so we still need to have truth tables. We're just going to now talk about what equivalent statements are. So equivalent statements basically means the answer columns are exactly the same. So notice it does not say that they're all true, right? So it doesn't say that they're tautologies, that they're all true. It doesn't say they all have to be false, and that's not a self-contradiction, right? It just says that they have to be exactly the same. So again, this is why it's so important to always follow those steps for setting up a truth table. Everything in alphabetical order across the top, right? And then the idea of cutting the first column in half, and then each column after that in half. That way you will always end up with things that are in the same order, so you can decide if the statements have the same truth tables, right? Have the same answers. So in example 1, I want to complete the truth tables to determine if not A, then not B, and if B, then A are equivalent. So just so we remember, since it might have been a couple of days, let's remember our truth tables. So I have true and true equals true. I have false or false equals false. And if I have starts true, ends false, equals false. So these are the three big ones, right? Make some flashcards, make sure you remember how those work. So here we go. So in my first truth table, we're going to do the not A, then not B. So I've got two letters. 2 squared means that I have 4 rows. So 1, 2, 3, 4. I need a column for each letter. So a column for the A, a column for the B. I need a column for each negation of a letter. So I have a not A and a not B. I don't have any parentheses, so I don't need a column for that, and so I can go all the way and do the entire statement, which would be that if not A, then not B. So now I can cut the column in half. Half of them are true, half of them are false, and then second column, each of those in half again, so true, false, true, false. Now I can actually do the operations. So I have a negation of A, which means basically the opposite of A. So I'm going to look at A, which is true, true, false, false. I'm going to do the opposite, and so that would be false, false, true, true. Then I want the negation of B. So again, I look at B, true, false, true, false. I do the opposite, so that would be false, true, false, true. And now I can do the final part, which is my conditional, my if-then. So from my little cheat sheet over there, it says true, then false, equals to false. I'm looking just at the not A to the not B. I want the one where I start true and end false. That's my false one. Everything else will be true. So be very careful. I know it says if B, then A, but I need to be in exactly the same order as I was in the first one. So that means I still will say 2 squared is 4, so 1, 2, 3, 4, and my letters are still A and B, so I have to put them in alphabetical order. Then what I want for my final is if B, then A. So now when I come down here, make a better straight line. Cut this in half. Half of them will be true, half of them will be false. I cut each half in half, so true, false, false. Now, the tricky part. This time I'm going to start at B and go towards A. So when I make my arrows, I'm going this direction. So if I wanted to think about it this way, it would look like true, then false, equals false, right? So when I look at the conditional, it starts at the true, it points towards the false. That's what makes it false, right? It's not an idea of left and right. It's an idea of what am I pointing at? what am I starting at, right? So I need to start true and end false. So now if I look, I start true on this one and I start true on this one, but the only one that I end false on is here. So that's my false one. Everything else is true. Now that I have those two, I can look at the answer columns. So answer column here, answer column here. When I compare those two, true, true, false, true, 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 false, true, they are the same. So they are equivalent. My math lab might say logically equivalent. And that's fine. They're the same. So whichever one you like better, equivalent, logically equivalent, they do mean the same thing. They do have the same value. So either one is fine. But the idea here is that I need those last columns to be exactly the same, in the same order. Everything about them, besides the like heading, right, should look the same. So in example 2, we are going to use De Morgan's laws. So the big things I need you to know about De Morgan's laws. Number 1, they only work for conjunction and disjunction. They do not work for conditional or biconditional. Okay, De Morgan's laws only work for conjunction and disjunction. And basically what you're doing with De Morgan's laws is you're distributing that negation, right? So it's just like distribution. I'm going to take the negation on the outside of the parentheses. I'm going to give it to everything inside, and I'm going to change the sign, right? So distribute negation. That's what it means, right? So give the negation to all variables and flip the sign between. So in example 2, it says write a statement that is logically equivalent to it is not true that tomatoes are poisonous or eating peppers cures the common cold. So probably it would help if it is not true, comma, that eating tomatoes are poisonous or eating peppers cures the common cold. So that comma there is what's going to tell us that this goes in parentheses, right? The is not true, that would be my negation on the outside. And then I have the or here, that's my disjunction. So now I can go about this like we have previously, and I can decide what my P is. So P would be tomatoes are poisonous, and Q would be eating peppers cures the common cold. And then I can put those things together. So when I look at this and I put these two things together, it says it is not true that, so negation, tomatoes are poisonous, P, or disjunction, eating peppers cure the common cold, Q. So now I want to write a statement that's logically equivalent, and I'm going to do this by using De Morgan's laws. So De Morgan's laws we looked at with sets, right? And we looked at how when I distributed that negation and changed the sign, the pictures were the same. They had the same meaning. They gave me the same set of numbers, right? So the same thing is true here. I can use De Morgan's laws to write in a statement that has the same truth value, the same meaning, right, as the original statement. So again, De Morgan's laws means I take this negation, I distribute it, I give it to everything, and I change that sign in the middle. So to write an equivalent statement, I would say not P and not Q. So the 3 lines, remember, means equivalent to. It's a way to write it without having to use the words. Now that I know what the symbols look like, now I can go back and write the sentence. So P was tomatoes are poisonous. So not P would be tomatoes are not poisonous. Tomatoes are not poisonous. This time our or changed to a conjunction. That's an and. So and. Eating peppers cures the common cold. I want the negation of that. So eating peppers does not cure the common cold. So these two statements are logically equivalent. They have the same truth values, right? They may not really sound the same when we hear them in the English language, but if we look at what they actually mean and their truth values, they have the same basic meaning. So now we've looked at 2 ways that we can show that things are logically equivalent, or that we can write statements that are logically equivalent. One is to make the truth table, right, and compare the 2 answer columns. That will tell us if 2 statements are logically equivalent. I can also use De Morgan's laws, right, so I can distribute that negation, change the sign in between, and that will let me see a statement that is equivalent to the other one, right? And then the third way to do this is if I have conditionals. So again, De Morgan's laws only work for conjunction and disjunction, right? Only for an and or an or. If I have a conditional, an if then I can use the idea of logically equivalent statements, right? Or related statements to find out what things are logically equivalent. So what we're going to talk about here are an original conditional, its converse, its inverse, and its contrapositive. So the original. An original statement is always just the basic if P, then Q. Then I have a converse. And the converse of the statement just changes my order. So now I'm if Q, then P. Right, so order changes. After that, I have an inverse. With an inverse, the original order stays the same, but now I'm going to negate both. So this would be if not P, then not Q. So I go back to the original statement. So always when I talk about a converse, an inverse, and a contrapositive, I'm talking about doing something to the original statements, right? So with the inverse, again, order stayed the same. I just negated both. So we're going to say negate both. And then the most important one, the one that you're going to use to help you with your project, is called the contrapositive. And with the contrapositive, basically I take the converse and the inverse at the same time of the original. So I'm going to change the order and I'm going to negate both of them. So this one's going to look like if not Q, then not P, right? So change order and negate both. So why these are important to us? So these are important to us because an original statement and its contrapositive are logically equivalent. if we go back to the very first example that we did, basically we had a statement and we had its contrapositive, right? So if we let this be our original statement, P then Q, I'm going to switch the order, right? So now I've got the Q first negated and then the P second negated. I had a statement and its contrapositive. They were a statement and its contrapositive, and when we did their truth tables, they came out to be logically equivalent. They had the same truth values, right? So we know that an original statement and its contrapositive are logically equivalent because we already proved it. We already made that truth table. So now if we come back down here to example 5, we know that the original statement and its contrapositive are logically equivalent. And then what I'm going to tell you is that the converse and the inverse are also logically equivalent. If you'd like, you could use a truth table and you could prove this just like we did with the others, right? But I'm just telling you that those two are logically equivalent to each other. So now what we're going to do is we're going to use this idea of the related statements, right? And we are going to write the converse, inverse, and contrapositive in example 5. The biggest thing with all of these things is always start with if. This will probably be like the #1 mistake that people make on their project and on their exam, is that when you do the converse and the contrapositive and you change that order, you want the if to stay with the first part, and that's not how this works, right? When I write the converse, it changes from if P then Q to if Q then P. The if does not get stuck to the statement. The if is based on the position. The first part is my if. What the arrow is pointing to, that's my then, right? So it's always starting with if. So here we go. I have an original statement. My original statement is if a whole number ends in 3, then it is an odd number. So if I want the converse of that, for the converse, I'm just going to change the order, right? So it still starts with if, always starts with if. But now I'm going to have the second part. So if it is an odd number, then now I'm going to write the first part. It is a whole number that ends in 3. So again, starts with the if, then is in the middle, right? Now I can write the inverse. So the inverse, I go back to the original statement. So if a whole number ends in 3, then it is an odd number, and I just negate both of them, right? So if a whole number does not end in 3, then it is not an odd number. So again, starts with the if, then is in the middle, right? And now for our friend the contrapositive. So now I'm going to do both. I'm going to change the order and I'm going to negate them both, right? So now it's going to start if it is not an odd number. So still starting with if it is not an odd number, then it is not a whole number that ends in 3. So again, if always, we start with if. Second part is the then. So since this has to do with numbers and math, we can actually decide if this is true or not, right? So if a whole number ends in 3, then it is an odd number. So all of the numbers that end in 3, 3, 13, 23, 33, 43, 53, 103, 1003, all of those would be odd because they end in 3, right? So this original statement is true. If I look at the converse, if it is an odd number, then it is a whole number that ends in 3. So now odd numbers, right? So odd numbers would be 1, 3, 5, 7, 9, 11, 13, 15, 17, 19, right? So when I look at all those odd numbers, do all of them end in 3? No, right? So that means that the converse is not true. If it's an odd number, then it is a whole number that ends in 3. No, it could end in other things, right? So my converse is false. When I look at the inverse, it says if a whole number does not end in 3, then it is not an odd number. So we just said I can end in 1, right? 11, 21, 25, 37, 49, right? All of those are still odd numbers, and they don't end in 3. So if a whole number does not end in 3, does that mean it's not an odd number? No, this is also a false statement. So when I look at the contrapositive, it says if it's not an odd number, then it is not a whole number that ends in 3. So if I'm not odd, that would be an even number, right? So even numbers would be like 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, right? So do any of those numbers end in 3? No, right? So this is actually a true statement. If it's not an odd number, then it's not a whole number that ends in 3. So this is true. So this is another way that we can see that the original statement and its contrapositive have the same logical outcome, right? They have the same meaning. And the same thing for the converse and the inverse. They have the same logical outcome, the same meaning. So what I need for you to take from this, in your project, the very first thing that I'm going to ask you to do is to find some ads and to write those ads as if-then statements. If you buy this product, then this will happen, right? So that's usually how most ads are built. If you buy our car, then girls will like you, right? If you wear this perfume, then guys will be attracted to you, right? That's basically how most ads are built. So that's what I want you to do. Find some ads. There are examples of the ads in eCampus for you to look at. And then I want you to change those ads into a conditional statement. If you buy this specific product, right? So you have to be very specific because that's what the ad is selling. It's not selling like perfume in general. It's selling one specific perfume, right? It's not selling foundation in general. It's selling a very specific foundation. So you have to be specific about this, right? So if you buy this thing, then what things will happen to you? What is the ad saying? Once you do that, I want you to write the converse, the inverse, and the contrapositive, right? So just exactly what we did here. I want you to write the converse, the inverse, and the contrapositive. It always starts with if, right? And then after you write those, I want you to think about the truth value of the original statement and of the converse and the inverse and the contrapositive. So the way that this is going to work for your project. Step number 1, compare original and contrapositive. If they are not both true, then neither is a valid statement. They both have to be true, right? First, they're both true. If they're not both true, then neither is a valid statement. So this will help you when I ask you if the original statement that the ad makes is valid, right? So the reason that they make the ad look like they do is because it could be possible, right? You could wear the perfume and guys could like you. You could buy the car and girls could like you, right? But when you look at the contrapositive, if guys like you, then you wore the perfume. Is that necessarily true? Is there no other reason a guy could like you besides you wearing the perfume, right? If that last statement, if your contrapositive is not also a true statement, then neither of them is true, okay? So when I ask you to tell me if you think the original statement is true or false and why, that's what I want you to do. I want you to compare the original to the contrapositive and decide if they have both true values, right, and therefore are valid, or if one of them is false and therefore both of them are false. After you do that, you're basically going to do the same thing with the converse and the inverse, right? So since they are logically equivalent, in number 2, I want you to compare converse and inverse. Same thing. If they are not both true, then neither is a valid statement. So this is how you can use converse, inverse, contrapositive really anywhere. You can use it to evaluate ads. You can use it to evaluate statements that other people say to you, right? So on the news, when they say, oh, if this happens, then this is going to happen, you can actually think about that logically now and say, well, if that doesn't happen, does that mean necessarily that the first thing didn't happen, right? So those are the things that you can use the logical equivalency for to help you determine if what people are saying to you is actually true or not.